Okay, so last time we proved the Riemann-Roch theorem. Maybe let me recall it. So there was a prerequisite that for any locally free, the same as torsion free, coherent sheaf F on a smooth projective curve C of rank R. The first cohomology with coefficients in this sheaf is finite dimensional. This was just a prerequisite, and in particular, the dimension of the first cohomology with coefficients in the structure sheaf is dubbed G, the genus of our curve. And now, well, also we define the Euler characteristic of F as the difference of dimensions of the zeroth cohomology minus dimension of the first cohomology. It makes sense because of this deep finiteness statement that the first cohomology is finite dimensional, and zeroth is also finite dimensional. And now, granted this, the Euler characteristic of our sheaf can be computed as the degree of the top exterior power, which is an invertible sheaf line bundle. So we know what is the degree, plus rank times 1 minus G. Okay. And we proved this. And while proving this, namely while proving the finite dimensionality of the first cohomology, we also proved sort of part of self-duality. So I wonder, what should I do first? Okay, well, let me first formulate the self-duality, and then I will recall something we proved last time. So now the next big topic is self-duality. And well, the statement is as follows. So first of all, there is a canonical isomorphism the first cohomology of our curve with coefficients in the sheaf of differentials is canonically isomorphic to the base field. Not that it's just one-dimensional, but there is a particular canonical isomorphism with the ground field. Okay, and now again, for any torsion-free sheaf F on our curve, we can take the first cohomology of our curve with coefficients in F. And also we can take the zeroth cohomology of our curve with coefficients in F dual tensor omega C. Okay? And then we can just well, we have a natural multiplication to the first cohomology with coefficients in the tensor product of these sheets. F tensor F dual tensor omega C. And then from F tensor F dual, we have a trace morphism just to, or I don't know how to say, evaluation, whatever. Morphism to just the structure sheaf. OC tensor omega C. But now the tensoring with a structure sheaf is nothing, so it's just the first cohomology of. Oops, sorry. First cohomology with coefficients in the sheaf of differentials, and we know that this is just the ground field, and so we obtained some pairing between those two finite dimensional spaces. First cohomology with coefficients in F, and zeroth cohomology with coefficients in F dual tensor differentials. And the claim is that this is a perfect pairing. Okay, so these two spaces are canonically dual. If we dualize this, then it is canonically isomorphic to zero homology global section. Yes.
Почему мы вот пишем когомология дуальная, а не пишем, что это гомология, например?
Well, we didn't study any homology theory yet, and we're not even planning to do this. We only have cohomology theory. Well, this is the statement of duality theorem, and just let me make a remark that the same.
Я имею в виду, что если когомологию дуализовать, то в топологии это гомология получается, а здесь мы
right. And here
избегаем.
Right. So the same claim holds true for any smooth projective, say irreducible variety of dimension n, and then there is a duality between ith cohomology with coefficients in F. It's a locally free sheaf, coherent sheaf. And there is n minus ith cohomology with coefficients in the dual tensor certain thing, and there is a pairing into the ground field, and this is a perfect pairing. And here this is called the canonical invertible sheaf. Or also sometimes.
I'm sorry.
Yes.
About terminology. Is
Yes.
it the same as so-called dualizing sheaf?
Right, absolutely. So it's also called canonical class. Also, as Daniel said, dualizing sheaf. And maybe there are some other names. But the definition is that this omega x is the determinant of the first differentials. So it's the top, namely nth exterior power of the color differential. Okay. So this was the statement of Serre duality theorem for arbitrary smooth projective variety. We only prove it for curves so far. But then we will also prove it for projective space, just for Pn. And in fact, it is not too far from Pn to arbitrary projective variety. So now let us start the proof of this Serre duality. And at some point, I will have to recall something from the last week, but at least let's first define this canonical trace morphism. So, well, from your home assignment or from the Riemann-Roch theorem, we know that for a line bundle, well, invertible sheaf, M on our curve C, the first cohomology will vanish if the degree of M is sufficiently positive. Maybe, well, maybe it's not immediately directly from Riemann-Roch theorem, but then from our proof. So when we prove the finite dimensionality of the first cohomology, then in particular this follows. Okay, so there is some extremal degree, the maximal well, say D, and an invertible sheaf M of this degree, such that the first cohomology with coefficients in M is still not zero. Okay, and in fact, we will soon see that this degree is 2G minus 2, and this M is the first differentials sheaf, the dualizing, the canonical class. Okay, but so far we only pick such M, and then for any point in our curve, we have the exact sequence. Like this, the skyscraper sheaf, and we know that M twisted by the point C, M of C, has a bigger degree, so has zero cohomology, and so it implies that the coboundary morphism
Извините, пропустил. Почему сдвиг на одну точку дает мне нулевые когомологии?
We chose our M such that any sheaf of bigger degree has zero first cohomology. In particular, M of C has degree 1 bigger and has zero cohomology.
Спасибо.
Okay, so this coboundary homomorphism is an isomorphism, delta C, from the global sections, if you want, with coefficients in this skyscraper sheaf into the first cohomology of this extremal sheaf M. Okay.
But it is only a surjection, as far as I understand.
It is only a surjection, and you will have the so in principle you could have, okay, let's write this. You could have the zeroth cohomology of M, then zeroth cohomology of M of C, and then this. But if it is a surjection, then you could take M of C for your sheaf M and continue so on. But so it will contradict our assumption that M has the maximal possible degree with non-vanishing first cohomology. Okay. Okay. So we see that this is an isomorphism for any point C, and now let's recall some part of the argument of the last Thursday. Well, I'm afraid we'll have to move to the next page.
Again, can you please explain why is it injective?
Why is it injective?
Yeah.
So otherwise, we will have. Well, let's write this sequence 0 to the global sections of M, to the global sections of M twisted, to the global sections of this skyscraper. Okay, and then this is 0, so we know that it's surjective, and if it is if it has a kernel, then the global sections of twisted sheaf is bigger than the global sections of M, right? And this is impossible because we know that the Euler characteristic is the Euler characteristic of M of C minus 1, right? And we know that the first cohomology of M is bigger than the first cohomology of M of C, right? But by assumption, and so the global sections must be the same. H1 of M is strictly smaller than H1 of M of C, and hence H0 of M must be equal to H0 of M of C. Okay. So where were we? We had this co-boundary morphism for any point C, and now I want to consider them all together, and that's what we did last time. So let me recall from the last time. We considered the following short exact sequence: 0 to first projection of M on the square of C, to the first projection of M twisted by the diagonal, and the first projection of M twisted by the diagonal, restricted to the diagonal. Okay, so here we have C times C. There is first projection to C. There is second projection to C, and there was diagonal embedding from C to the square. Okay, and then we obtained the co-boundary morphism, just so to say, the variation of the co-boundary morphism at a point from the previous page, the variation as the point moves along the curve. We obtain from delta, from the push-pull. Okay, to the first direct image. Okay, but since it was push-pull, then this is nothing but the first cohomology of M tensor the structure sheaf of C, and the and we can also compute the left-hand side. So for the left-hand side, we know that the structure sheaf of the square twisted by negative diagonal, restricted to the diagonal, by definition, is the sheaf of differentials, and hence the push-pull is just M tensor the dual. Sorry, sheaf. Sorry, the dual. For me. Okay. That's it. So our co-boundary morphism is from M tensor the dual sheaf of differentials to the first cohomology with coefficients in M tensor.
Можно спросить?
Structure sheaf. Yes.
Омега С минус первые элементы его сечения — это частные производные, ну, или что?
Well, this is the tangent bundle, if you wish.
Понятно, спасибо.
Fine. So this is what I need, and now I know that the first cohomology. So let's. This was the recollection from the last Thursday about arbitrary torsion-free sheaf M. Okay, but we are applying it to one specific sheaf M that had the maximal degree with non-zero first cohomology. Okay, and we know that the first cohomology is one-dimensional, so this is an isomorphism for any C. Okay, so the fiber of delta at any point in the curve is delta C, an isomorphism. Hence, we see that M tensor omega C inverse is isomorphic to OC, and hence M itself is isomorphic to omega C. Okay, very good. And in particular, for any point, we have a canonical generator in this. I mean, this H1 of C with coefficients M was isomorphic to just look here to the sections of the sheaf M of C relative to C. Okay, and if you take the canonical generator of this space, you get the canonical generator of the first cohomology. Okay. Okay, so this is a canonical isomorphism. Okay, so in particular, well, let's say the corollary of this argument that the first cohomology of our curve with coefficients in the differential sheaf is canonically isomorphic to the ground field. Okay, that was part of Serre duality statement, and that part is proved, and we have to proceed for duality for arbitrary sheaf. Okay, so now take F arbitrary locally free sheaf on our curve, and let me recall what we're proving. We take any morphism alpha from say the global sections with F dual tensor the canonical class, and this is the same as just homomorphisms from F to this canonical class. Okay, and since we have a morphism from F to the canonical class, then it gives rise to some morphism on the first cohomology. So by the naturality of H1, we get a morphism from H1, the first cohomology of F, to the first cohomology of the dualizing sheaf that is canonically equal to the ground field. Okay, and let's denote this morphism by the first cohomology of alpha. Okay. So we obtain the morphism that we dub H1 from the global sections of C with coefficients in F dual tensor dualizing sheaf, the same as morphisms from F to dualizing sheaf. Two homomorphisms from the first cohomology of F to the first cohomology of the dualizing sheaf. This is the same as just the dual space of the first cohomology. Okay, so now the third theorem states that this morphism is an isomorphism. So we will prove that H1 is an isomorphism. Okay, once again, from global sections of the dual sheaf twisted by the dualizing sheaf to the first cohomology of our original sheaf F dualized. And this is the origin of terminology dualizing sheaf. Okay, the twisting by this canonical class omega C leads to dualization of cohomology. Okay, so let's prove this, and we need the following reformulation. So we have this coboundary morphism, delta here. Okay. So let's apply it in two situations. So first, it can be applied to the case when our sheaf is just the dualizing sheaf itself, and then we get the dualizing sheaf tensor the dualizing sheaf, and certainly this is just the structure sheaf, but we rewrite it as the first cohomology of dualizing sheaf, that is the ground field K anyway, tensor OC. Okay, so here tensoring is over the structure sheaf, here is the over the ground field. Okay, and also we can do the same for our sheaf F. So we'll have F tensor the dual sheaf of differentials, and there will be a morphism delta as well to the first cohomology tensor OC, just what we recalled at the previous page. And here we have our morphism alpha tensor 1, and here we'll also have something. So let me say, what do I mean? So here alpha is a morphism from F to the dualizing sheaf, and the lambda is a morphism from first cohomology to first cohomology. Okay, and what is the claim? That if this diagram commutes, then for any alpha there is a unique lambda like this, and for any lambda there is a unique alpha like this. So if the diagram commutes, then for any alpha there is a unique lambda. Well, to make the diagram commutative, and conversely, for any lambda there is a unique alpha to make the diagram commutative. Okay, so well, this is maybe a fancy reformulation of what we need to prove, right? Because well, I don't know even what to say. Well, for example, in the top row you have an isomorphism, right? And well, what shall I say? So it implies that if for alpha there is such lambda and there is unique such lambda, then the morphism H1 we're studying is surjective, and if for lambda there is a unique such alpha, then the morphism H1 we're studying is injective. Okay, so it's just a fancy reformulation of what we need to prove. Okay, so now let's prove this fancy reformulation. Although unfortunately I have to turn the page. But okay. Okay. So for any lambda there exists unique alpha since the top row is an isomorphism. Let's have a look. Yeah, so you just well, you stare at this, yeah, and you define alpha just as the composition of the bottom row and lambda. Okay, that's clear. Now for any alpha there exists unique lambda for the following reason. So well, again, let's have a look here. And all those co-boundary morphisms, the delta, in the top row and in the bottom row, they are compatible with the restriction to any point of our curve. And for a point of our curve, the source of this co-boundary morphism is one-dimensional, right? It was from some fiber at the small point C to the first cohomology. The fiber at small point C for invertible sheaf was just one-dimensional, and so there is nothing to prove. That's a natural diagram, and certainly it commutes. So once again, if you restrict it to any point C, then it's clear. So it implies that given alpha, lambda is defined on the image of let's say delta C for any point, and hence on the sum of these images okay, so I can choose various points, and for any of them, lambda will be defined on the image of one particular thing. So it will be defined on maybe I should not say direct sum. I should say just sum, because they can have linear dependencies in the image. Okay, so we only have to check that those guys generate the whole first cohomology. Okay, and then it suffices. Sorry. To find a few points, C1, so on, Cn, such that the first cohomology with our sheaf twisted by the sum of those points will be 0. Right? Just from the long exact sequence of cohomology. Okay. But now last Thursday we proved as sort of a trivial part of CR duality. When something was 0, the would-be dual thing was also 0, right? 0 equals 0 dual, if you want. Okay, so it suffices to check that the global sections of a twisted dual sheaf negative C1 minus Cn is 0. Okay, and now we are done, because we know that well, we start with no points. We know that there are finitely many sections of this dual twisted sheaf. So say, let's call it n capital, and now we are untwisting by various points. So to take a section S1 in here, then well, it's not 0, so take a point C1 such that the value of S1 at this point is not 0. But then when we untwist our sheaf by C1, it imposes a non-trivial condition, right? Because we did have one section that was not vanishing at this point. Then vanishing at this point does impose a non-trivial condition, and hence the dimension of global sections with coefficients in this slightly untwisted sheaf is less than n. Okay, and if it's still bigger than 0, then we continue like this. Till we get.
То есть условие неравенства нулю сечения накладывает ограничение на размерность сечения вот этого пучка, да? Поэтому меньше n.
Yeah, because we did have a section that was not vanishing. Well, if all our sections were vanishing at this point, then when we write negative C1, it imposes no conditions, because negative C1 is just means take all sections vanishing at point C1. If all sections vanished at the point C1, then we would have really no condition. But if there was a section not vanishing there, then it does impose a condition, and imposing sufficiently many conditions, we obtain the desired vanishing, and we're done. So congratulations. So this is a very powerful package. Riemann-Roch plus Theorem. And in particular, you can now reformulate Riemann-Roch using Ser by saying that for locally free sheaf F of rank R, sorry, and degree of determinant D, the dimension of global sections of this sheaf minus the dimension of global global sections of the twisted sheaf, dual and twisted by dualizing sheaf, is D plus R times 1 minus G. Okay, and it's pretty often used in this form. So we now can prove one claim from the home exercise, that for any point in our projective curve, the complement is affine. And the proof is immediate, because for very big n, we will have the Euler characteristic of the sheaf twisted by this point with multiplicity n will be positive, and hence the global sections will be positive. Well, we need a non-constant function, so we need bigger than 1. But use bigger than 1 here too. Okay, and hence there is a non-constant function f on C with poles only at this particular point. And then we had a lemma some time ago that in this situation the complement is affine, so it's regular. Okay, and it is not constant, and hence the complement is affine. Okay. So in other words, there is a stupid dichotomy. Any curve is either projective or a phi. Well, say small.
Кривая проективная рассматривал.
So far, yeah, the Riemann-Roch theorem makes sense only for projective curves. Otherwise, the zeroth cohomology are infinite dimensional. There's no first cohomology, but the zeroth cohomology are infinite dimensional, so you cannot formulate the statement. So any smooth curve is either projective or a phi. Okay. Now, the other immediate corollaries are as follows: that the dimension of global sections of differential sheaf is G. This is the same as dimension of the first cohomology of the structure sheaf, just because those two spaces are dual. So that's by their duality. And then you know that the degree of the dualizing sheaf is 2G minus 2, as Sergei was eager to know. Okay, and now the next very important corollary is the Riemann-Horvis theorem. So we have a morphism F, or maybe pi, I don't know, from one projective smooth curve to another one. So then twice genus of the upper curve minus 2 is the degree of our covering pi. Yeah, maybe I should say that pi is not to a point, so it's dominant. Okay, so the degree of this covering times twice genus of S minus 2 plus the degree of the divisor of the relative canonical class. Well, we defined this thing. Maybe let me say one word. We have the following exact sequence: 0 to the pullback of the canonical class on C. Then there is this differential to the on S to the canonical class on C, and then the quotient with relative differential sheaf.
Что такое F маленький индекс?
Pardon me?
F маленький индекс у дифференциала.
Oh, sorry, it's pi. Sorry, it's pi. Thank you. And this is a torsion sheaf. Okay. Well, this two genus minus 2, probably you know that it's the Euler characteristic of your curve, say topological. So well, let me say, if our ground field is C, the topological Euler characteristic of the Riemann surface C, for example, is 2 minus 2g. Okay, and so the Riemann-Horvis theorem says that the Euler characteristic of well, maybe let me write it this way: the topological Euler characteristic, not to get confused with the Euler characteristic of coherent sheaves we had before. The topological Euler characteristic of C equals the topological Euler characteristic of the base curve S times the degree of our covering minus degree of the divisor of relative differentials. So this measures the ramification. Okay, and probably you all heard about this Riemann-Horvis theorem, and you know its topological proof via triangulations. Yeah, but it's very well, very important that you can prove this theorem in the absolutely different world. Yeah, and there is one proof topological, so to say elementary, and there is another proof algebraic geometrical, which makes sense over arbitrary fields, say of finite characteristic, for example. And I find it very impressive and exciting that there are some statements that have very different proofs. So that's very convincing that you have the different proofs of the same statement, then it must be true. Okay, so let's prove this, and this is immediate. So we know that the canonical class upstairs is the pullback of the canonical. Sorry, always. The canonical class downstairs, but twisted with the divisor of the relative dualizing sheaf, and hence the degree of the canonical class upstairs is the degree of pi times the degree of the canonical class downstairs plus the degree of this divisor. And well, that's it. Nothing else to prove. Fine. Now we can well derive something for just double cover specialization. Well, the particular case when the degree of pi is 2. And what do well, how do you construct double covers? Well, it's easy to write them all down explicitly, so to say. So then C is the normalization of S in a quadratic extension K over the field of rational functions on S. Okay, and any such extension is obtained by adjoining a square root of some function f but it's not quite true. Can anyone say what is my mistake? What could be wrong? No, nobody knows. Well, unless the characteristic of K is certainly true, and then you may need f squared plus f plus plus some function x is 0 for x function on the base. Okay, but maybe let's say the characteristic of K is not 2 to be on the safe side, and then then we just extract a square root of some element in the some function downstairs. Now this f, well, how to say it? Okay, say f. Well, we may choose f having well, all the zeros and poles simple. Okay, because otherwise you just multiply by the square of some local element, and the square root will not change. Okay, so the divisor of f will be C1, sorry, S1 plus so on plus S n minus S prime 1 minus so on minus S prime n, and these are all distinct.
Числителя и знаменателя одинаковое количество слагаемых должно быть.
The degree of principal divisor must be 0, right?
Да, спасибо.
Yeah. So the Riemann-Horvis theorem in this case is very simple, just because the ramification divisor is also very simple. It's only double cover, so it's either unramified at all or it has a ramification index 2. Okay, and then if the ramification index is 2, then the multiplicity of this divisor of the relative canonical class is just 1. And so, well, let me write it down. The ramification indices over S I and S I prime are all E equals 2, and all the rest are non-ramified. And so it means that the genus of the covering curve is the genus of the base curve plus 1/2 of the number. Well, maybe let me write down n plus n minus 1. So this n, once again, is the 1/2 of number ramification points. So in particular, number of ramification points is always even. Okay, and also in particular, if the genus of the base is 0, so the base is just the projective line, then the covering curve C is called hyperelliptic, and you will have the home assignment about hyperelliptic curves today. So it's called hyperelliptic because if n is 2, then the genus of C is 1, and C is elliptic. So in a sense, hyperelliptic curves are just higher genus analogs of elliptic curves, though not in many respects. For example, elliptic curves are algebraic groups, as you know, but higher genus hyperelliptic curves are never algebraic groups. In fact, there are no more algebraic groups, just elliptic curves and multiplicative group and additive group, nothing else. I mean, for curves, there are just 3 types of one-dimensional algebraic groups. Okay, so that's
Sorry.
yes.
So what is the difference between multiplicative group and additive groups?
Well, I don't know how to answer such a question.
Like, what do you mean that
what is the difference between a dog and the cat?
Huh?
What is the difference
Pardon?
between a dog and the cat? So while you're pondering this deep mathematical question, we'll continue. Okay. So now let's consider. Yeah. By the way, when we studied the previous Riemann Horvis theorem, I never mentioned that I wanted it to be not everywhere ramified. So I wanted to be separable. Let me write it down. Dominant, separable. Morphism. Okay, and now let's study inseparable morphism. So suppose phi is purely inseparable. Then genus of the covering curve is just the genus of the base curve, and the proof is immediate. Just recall that we classified all the purely inseparable morphisms. They were just Frobenius morphisms. say degree of pi is q. This q is the characteristic of our base field to some power n, and then this pi is necessarily the Frobenius, this q Frobenius, and it's essentially from S to itself. You may well rename one of these as you wish, but it's essentially from S to itself, so they have the same gender. Now, if we have a general situation, we can decompose our morphism into the composition of purely inseparable and separable. Then let's have the following general statement that if the genus of the base curve is at least one, so it's not a projective line. Then the genus of the covering curve is bigger, and the equality can happen only if the genus over S is 1, or pi is purely inseparable. Okay, so since elliptic curve of genus 1 is a group, then certainly have many morphisms from this group to itself, for example. Yeah, just multiplication by some number. No, taking any point to its multiple, nth multiple. And it will have degree, if it's nth multiple, then it will have degree n squared. Okay, so such things happen, but they only happen for elliptic curves. Otherwise, the genus of the covering will be strictly bigger than the genus of the base. The proof is again immediate. So we decompose pi as the composition of e to some intermediate curve e to the base s, and this will be, say, gamma. It will be purely inseparable. And this will be say eta, and this will be separable. Okay, and now, but by the previous claim, I may assume that pi equals eta, because purely inseparable, that does not change anything. I mean, does not change the genus, and hence by Riemann Horvis, we see that twice genus of C minus 2 is at least twice genus of S minus 2 times the degree of pi. Yeah, there will be some correction in the degree of the relative canonical class, but we only need this very rough estimate, and since degree of pi is at least one, then we're done.
А если GS равно единице, почему равенство возникает родов?
Because then 2G minus 2 is 0.
2GS минус 2 будет 0. Ну, получится 2GC минус 2 больше или равно нуля. Почему тогда GC равно единице?
No, sorry, maybe I wrote something stupid. What did I write? If the genus so if the genus of the base is 0, then the genus of the cover can be also 0. That's true. And if the genus of the base is bigger than 0, then it'll be a strict inequality. Yeah, so I think that that's evident. I don't what's the question once again? I don't see any problem.
Я так понял утверждение, что если GS равно единице, то GS равно GC. Так?
It can be so.
Может.
The statement is that if the genus of the base is bigger than 1, then the genus of the covering curve is necessarily strictly bigger than the genus of the base. Right?
Равенство GS равно GC может возникать только когда GS равно единице.
Right. So if pi is separable of degree bigger than 1, and the genus of the base is bigger than 1, then the genus of C, is bigger than the genus of S. Okay, and now the most immediate and stupid corollary, but it's actually important and interesting, and it's called Leroy theorem. In dimension 1, says that if we have a dominant morphism from a projective line, from the projective line to some curve S, then S is necessarily isomorphic. Well, let me say genus of S is 0. So it's absolutely isomorphic to P1, but not via this morph. Yeah, it can be covering of arbitrary degree. So S is abstractly isomorphic to P1 as well. And so pi is just a rational function on P1. Okay. So in fact, well, if dimension is 2, and we have a dominant morphism pi from P2 to some surface S, then S must be rational I mean, there is a birational isomorphism abstract from S to P2. But if dimension is bigger than 2, then this is wrong. But the very first counterexamples were found maybe only like 50 years ago, in 70s. Okay, so this Leroy theorem that does not generalize to very high dimensions, but it is very, very deep. The counterexamples are very involved. It's, let's say, at our present level, there is absolutely no hope to construct a counterexample. Okay, so that's it for today. Next time we will discuss residues of differentials, rational differentials on curves, and then we'll go on to higher cohomology of higher dimensional varieties.
Можно спросить?
Yes.
На странице 4 было утверждение, связывающее сечение с хомом.
Yes, but now I was taught a few unpleasant lessons, and I will not go to page 4 because otherwise I will not be able to save my notes. They will be saved empty. So do not tempt me to go to page 4. I will not do this.
Можно я тогда переформулирую сейчас более
Oh, yes.
простым? Сейчас, одну секундочку. Ну, вот сечение омега С на кривой С можно переписать как хом из омега С, из ОС в омега С.
Oh, yes, absolutely.
Вот почему это так?
Just by definition, for any sheaf at all, the global sections of any sheaf F, absolutely any sheaf of modules over the structured sheaf, are the same as homomorphisms from the structured sheaf to F. Because given a section, you send the section 1 of the structured sheaf to this particular section. And conversely, it's the same.
Спасибо большое.
Welcome. Okay, then I'm saving the note. I'm stopping the recording and see you Thursday.
До свидания.
До свидания.